Welcome. This is a tutorial for the derivative test. So just to remind you, this is our function. This is the interval of our function. If I told you in this interval, what is the maximum and minimum value? So you look here, that's obviously the maximum value at an endpoint. What is the minimum value? The minimum value would be here in this interval. Yeah. If I told you what are the local minimum and local maximum points, so we have two local minimum point. This one is a critical point and this one is a singular point, and we have one local maximum point which is critical point. Then here we have an inflection point. These are endpoints. Why derivative? There are a group of optimization method called derivative based method, and in this derivative based method what you do, you see, let me show you. That's the main idea. When you find like the rate of a change or the first derivative is zero, that where you can locate mean, max, and some of the inflection point. Yeah. And then that you know this information from the from the first derivative, because the rate of a change here is zero. So you just find the first derivative, you equate it to zero, and then you find the root of the equation. Yeah. So it will be this one, this one, this one. And for this, if you want to know whether this is a local min, local max, or inflection point or local max, so if your second derivative evaluated at this critical point is less than zero, then this is a maximum point. If it is larger than zero, it's a minimum point. If it's equal to zero, that's like an inflection point. Here, these are singular point, and singular point usually the derivative here is undefined. So if your objective function has a lot of these singular point, this derivative based method might not work. So that's like a summary of what we did. But let's just solve an example here. Okay, so this is an example here, and let's just see how to do this. So I'm telling you, find the global. You can see the function here already, but let's assume you don't see this function. We don't know how it looks like. So just forget that you know. Forget that you know like this guy. Like okay, we don't know this guy. We didn't see this guy. Okay. Okay, we don't know this guy. We didn't see this guy. Okay. So how to solve this? So to solve this, basically, we need to find all the critical points, yeah? And then we need to evaluate also our endpoints to know the maximum and minimum, yeah? So let's do it, yeah? So how to find all our critical point, and then after finding the critical point, we need to evaluate each critical point. Is this a global mean, global max, or inflection point? Okay, so how to do this? So let's just remember we you how to start these problems. I told you like you just that's how you start them. You find like the first derivative and the second derivative. That's how you start. So let's look at this guy here. So this guy here, the derivative of this guy here, that would be like remember this is like for example v and this is u. So that would be like the derivative of this one times this one. So the derivative of this one is 1. uh, The derivative of this one is 1 times the derivative of this one. So this one, the derivative is 1 times the derivative of this. Sorry, times this one, not the derivative. So sine x squared, yeah. And then plus this guy, yeah, time like the derivative of this guy. So what is the derivative of this guy? So the derivative of this guy is like cosine x squared time like 2x, because you just the derivative of sine is cosine, and then you multiply it, you use the chain rule, so you multiply it by 2x, yeah. So basically, did I forget anything here? Uh, so that would be x, yeah, cosine x, yeah. So this will, I can simplify this to sine x square plus 2x squared cosine x squared, yeah. So I got something that looks like this. Okay, what is the second derivative? So the second derivative of, and then here this is like 0, yeah? The second derivative of like this guy here, so sine x squared, that would be like cosine x square, like time 2x, yeah? Plus here, so like this is a derivative of the first guy here times the second guy, then the derivative of the second guy times the first guy. So the derivative of this guy, that would be like 4x, 4x, yeah, cosine x squared plus 2x squared times the derivative of this guy. So the derivative of this guy, that would be negative sine x squared. So I'll put like here negative, here sine x squared times like 2x, okay? So can I simplify this a little bit? Yes, we should. So how can we do this? We have like 2 of this guy and 2 and 4 of this guy. So we have like 6x, yeah, cosine x squared, yeah, minus, I just multiply, so did I do a mistake here? So that would be, let me see what I did here. So here, that would be like minus 2x times sine x squared times 2x. So that should be minus 4x to the power 3 sine x squared. Yeah, that should be this guy here. Okay. So that's like my second derivative here. Okay. So now, how can I find so like all the critical point occurs where my this is equal to 0. So basically, I can say like sine x squared plus 2x squared cosine x squared, that is equal to 0. Yeah. But now here's the question. How could I find the roots of this equation? Like on the interval from -1 to -3. So obviously you cannot use like algebra, like algebraic manipulation. You cannot manipulate this equation algebraically to find the roots of this equation. So you have to solve it numerically. So you need to use a numerical solver. So the easiest way to do it is that you use Python. So use Python, you use any of the optimization algorithm, and then in Python, and you give it this interval, and it will find this roots of the equation in this interval. If you don't know how to use like MATLAB or Python or a programming language, you can do it with Excel. So let me uh, show you how to do this with Excel. Yeah. So to do this basically with Excel, I mean, it's tedious, but it is doable. Yeah, I mean, better than yeah, like nothing. So let me just get the equation uh, that we have here. Oh, I need to. Let me see if I can. Okay, let me just write the equation. So that is here my f prime of x. Yeah. And just like my x, yeah. And let's just say x is equal to minus 2. Here's the end, yeah, of my interval. So now this is my equation here. I need to type this equation here. So that is equal to what? I need to type this equation here. So that is equal to sine. Uh, here, like this guy, square. Like I'm typing this equation, yeah, plus 2 time. See what's going on here. Okay. So let's do it again. So sine, okay, this guy square plus 2 time this guy to the power 2 time cosine this guy square. Yeah. So basically, I have this guy written here, and like the objective is like what is the value of x? Yeah, that will make this guy is equal to 0. So you can do it by trial and error. Like so, this we have negative 5.9. So that you try minus 1.5. Yeah, sorry. Yeah. So you see, it's getting smaller. How about minus or like let's start from minus 2. Yeah. So minus 2. Yeah. You try minus 1.5. See, it's getting smaller. How about minus 1? It's getting larger. So I have one root between minus 1.5 and minus 1. So how about minus 1.4? Well, it's getting smaller. How about minus 1.45? It's getting larger. Then it must be maybe 1.3 or 1. Oh, see, now it's getting smaller and smaller. So you can just keep doing this with trial and error until like you make this guys equal to 0. Yeah. And then, but this is very tedious and not nice. Yeah. So one way you can do it, you can come here, you can go to what if like goal seeker, and then basically you tell him set this guy, we want this guy to be equal to 0. Yeah. By changing which guy? By changing this guy. Yeah. Then you do okay. So that's one of the root of the equation. So at negative 1.36, this guy will be equal to 0. Okay, you now you try like minus 1 because remember you just need to find in all these intervals. This is just one root. There could be so many roots. So and then you do this again. So minus 1. So like maybe let's make it smaller. Minus 0.5. See, it's getting smaller. Maybe minus 2. I mean, it's getting smaller. Minus 1. It's getting smaller. So again, this is very tedious. So one thing you can do, you can just do again goal seeker again. So how do you do this? You go here. So you go from data, what if analysis, go seek, and set the cell. I want this guy to be equal to 0 by changing this guy here. Yeah. Uh, so I got something like this. Yeah. Let's see. I mean, point 0, like something close to 0. Okay, so you can just do this until you find the end of your interval. But that's very tedious, and that's why we don't use Excel, and that's why we use like something like R or Python or MATLAB or something like this. So let me show you like this is with uh, with Python. So with Python, basically SciPy, so that is one of the most commonly used packages in Python. And then in SciPy, you use this optimization module and you use fsolve. You put your equation here, you tell him start from here, end from here, make like this guess, like these things that I was doing, like 50 of them, and then you solve your problem here. If the you solve your problem, you find like you do a loop, and then you go through all like start to end, and you keep, and this is the number of guesses. So remember like these trials and like these intervals that I was checking one by one. So here I have like I'm checking like 50 of them. Yeah. And when I found the root, I keep adding it to my list, then I print it at the end. And then if you run this, then I got like these 4 roots. Yeah. So let's just write this down. Yeah, so now these are my roots. I found them numerically, not algebraically as we did before. So if I equated uh, this guy like to 0, like to equate this guy to 0, my x value that will make like this guy equal to 0, okay, to make this guy equal to 0, x could be minus 1.36, x, or x could be like 0, or x could be 1.36, or x could be 2.19, or x could be 2.81. Yeah. So basically, any of these value of x will make this guy equal to 0. And these are like my critical point. And you can see here, so at minus 1.36, see, minus 1.36 here, like this guy, I have like a critical point. At x equal to 0, I have another critical point. At 1.36, which is here, 1.36, I have like another critical point. At 2.19, like here, 2.19, I have another critical point. And at 2.81, so here like 2.81, I have another critical point. But are these guys, like how would we know, like are these guys what are these guys like? Are these uh, minimum, maximum inflection point or what? So to know this, you just substitute like this guys, each of these guys in like this equation. If your x like critical is less than 0, you have like a maximum point. If your x critical is larger than 0, you have like a minimum point, like one of these, yeah. And if f of x is equal to 0, you have like what do you call it, like inflection point. And from this graph, because we plotted it, so we should expect to get how many of these guys? We should expect to get like 2 of these guys. We are expecting to get 2 of these guys uh, in the positive, and both of them here. And we are expecting to get like 2 of these guys, and we are expecting to get like 1 or something like of these guys. Okay, like these points. And we have 5 points. Okay, so we can just like do this again. Like if you like, you can do it with Excel, for example. So you can come here in Excel, you can put your critical point, which is, let me just like, so this is my f of x now. I'm evaluating for my f prime of x, but let me put like the values that we got here. So what did we get from Python? Let me just put this value here. Okay. This is like control C, yeah. You put them here, control V. I'll get rid of this guy. See, even this guy in Excel, it was not very accurate. That should be 0. It got like something close to 0, but not very accurate. But anyway, we can get here. Why this is not working? I don't know. Or maybe so this is equal to this guy, yeah, times this guy times this guy, and when I hit enter, I should get a 0. Well, I got something very close to 0, but ideally it should be, I don't know, maybe if I didn't get a 0, this means, okay, I think I know why, because, let me, because I'm approximating these numbers. That's why I'm not getting exactly 0. I'm just like showing like 2 decimal point. So let me show more than 2 decimal points here. So let me just show 10 decimal points, yeah. Uh, that's better, yeah. So you see here, I'm showing this with more decimal points. And that of course will give me more accurate answer, yeah. So if I put like, you come here, you paste these guys here. See, I got like 0 because I'm showing more decimal point. But I mean, to present your answer, you can just, yeah, you can do something like this. Just show. Okay. Now I want to find my second derivative. Like, how do I do this? How do I do my second derivative? So like to do my second derivative, I just like here have an equation for it, this guy. So that would be 6 times x, yeah, time cosine this guy square, yeah, minus 4 time this guy, so power 3 time, yeah, sine this guy square. And I know my first point is a minimum just from the graph, so I should expect to get a positive number here. I got a positive number here, yeah, that's correct. And then you do the same for all of them. I got a 0 here exactly as I expected at 1.36. See, like at 1.36, let's look here. It's just the visualization. So let's just see what we have here. So at negative here, my first derivative is 0. So the rate of a change here is 0. And like this is positive because I have a minimum. Here, this is like an inflection point. So my second derivative is 0. 1.36, I got a positive. So what does this mean? If I got a positive here, which like I should, that should be negative. And sorry. Yes, I got a negative. Yes, because you get like, yes, you got a negative because you have a maximum point. You got a positive here because you have a minimum point, and you got a negative here because you have like a maximum point. Yeah. Okay. So basically that's it. Yeah. One thing you also want to do. So basically, so I can classify these points. So my second derivative is positive. This means that this is a min, which is here. This is 0 inflection point, which is here. This is negative, maximum, minimum, and like another maximum here. Now, one more step which we didn't do, let me just move these guys, is to calculate the function itself, like the f of x itself. So the f of x itself, what's my function? uh, because we need this information. I will show you why do we need this information. We need this information because, so oops, let me just evaluate my function itself. Yeah. So f of x, the function itself, that's like x time sine uh, x square plus 1. Yeah, so I got something that looks like this. Let me check if this is correct or not. I mean, it's about right, yeah. We got negative zero point 0.3, so yeah, it's about right. And then I do it all the way. Let me check, like at 0, I should get 1, exactly 1, yes. Here I got like 2 point something, that's about right. Here I got negative 1 point something, and here I got like the maximum. But why am I evaluating this? I'm evaluating this because read the question carefully. Read what it's asking you to do. It's asking you what is the max, like in this interval, what is the maximum and the minimum. So the maximum and the minimum, it does not necessarily need to be one of these guys. It could be one of your endpoints. So I need to evaluate my endpoints. So I have like -2 and I have 3. So let me evaluate my endpoints here. So let me just do this here. So my endpoint, I have like -2, yeah, and I have like 3, and and I mean, I can do all these guys here, yeah, and this is like end point, and this is like end point, yeah. Okay, so what do I get here? So let's look at this table now. So here is my results. So let me just make them something like this. Oh, I don't know if you can read this. Make it a little bit bigger, yeah. Okay, here we go. So let's just look at this. So what is my minimum value here? So my minimum value here is this guy, yeah? What is my maximum value here? My maximum value here is this guy. So basically, the minimum and the maximum of this function in this interval is like -1.18, which is here at 2.81, yeah? Sorry, at 2.19, and the maximum in this interval here. It could be your endpoint, but this is not the case here. Okay, that's basically how that would be the answer for this one. That would be the answer for this problem. But you see here, if you can do that much, this means that you understand a lot about like these derivative-based optimization. You can find like you can you know what the roots of the equation, or you can find them analytically as we did before, and you can find them numerically as we did here. That would be like our results. So if you copy this guy, yeah, and maybe we have like yeah, so that would be our results, yeah. uh, yeah, just like that would be our that would be our results, yeah. Okay, let's do one more problem before we seem like the time is okay. So let's do this. This is similar to one of your homework problems. This is kind of simple problems that you usually get when you study optimization and derivatives. To give you these type of problems. Okay. So a manufacturer want to design a cylindrical can with a closed top. Uh, Cylindrical can with a closed top. Yeah. to minimize the material cost with a closed top and bottom. So it's a can that should be closed from the top and the bottom. The can must have a volume of. Okay, so here we have like the volume, yeah. So we have like an equation for the volume, and we know the volume is well, like what? So the volume is like pi r square h. That's like the volume. That's like 500. The cost of the material and the cost of the material for the bottom and the top is, and the cost of the side is. Find the dimension, radius, and the height that the can of the can that minimize the total cost of the material. Okay, so that is not so. What is the total cost? So the total cost would be the total cost of the top. Let me just plot it here. So you have like the top here and the bottom. The this guy here is $20 per centimeter square. This guy here is $10 per centimeter square, and this guy here is like $20 per centimeter square. So what is the cost? So the cost would be, uh, and this height here is like, we don't know this guy, that's what we want to find. And this R here, this like radius here, we don't know this radius we want to find. But we know the total cost, yeah? So the total cost is like 20 times pi r square, yeah? And like we have two of these guys, because like one here, yeah, and one here on the top, plus 10 times here, that would be pi 2 pi r h, yeah, 2 pi r, and like the height, yeah, 2 pi r h, and we only have one of it. So that's my objective function, subject to, so that is subject to this condition. That's my objective function. Okay, so let's just make this looks a little bit nicer. So like to make this guy look a little bit nicer, what we can do, we can say 40 pi r square plus, let me express everything in terms of r, yeah? So that's plus 20 pi r, 20 by r, yeah, and then here I can say that 500, so h is equal to 500 over pi r square, yeah. So like this guy can go with this guy, so like these guys can go together. So I got like here would be, and I can multiply this is would be 10,000, yeah. So I can get like 40 pi r plus 10, 1, 2, 3, 10,000 r to the power of minus 1, yeah. So I have something that looks like this. So remember, like the first thing you do, so this is your C of R. The first thing you do, you in this type of a thing, you do these guys, yeah. So you get like here 80 by R. You got here, this is minus 1, so minus 10,000. This would be minus 2, so that would be like R over 2, yeah, R over 2. So that is basically like we can, I mean, if you want to do this guy also now, we can do him now. So that's like 80 by this, and then here that would be, you multiply this by negative 2, and then you raise this by 1, so that would be like 21, 2, 3 over r cubed. Okay, so we have something that looks like this. Now, what we want to do, like we like to find like our critical point, we need to equate this guy to 0. So what we do here, we say like 80 pi r equal to 1, 2, 3 over r square. What does this mean? So like this this guy can go with this guy. This guy can go with this guy. So basically like sorry, it's the other way now. Sorry. See, don't see, it's like try make not to make this careless mistake. So basically this guy is multiplied by this guy, not go like see this are on the opposite side. So here you got like 80 pi r cube 1, 2, 3, yeah. So you did something like this, then you can what you can do, you can say like r square. So this will go away with this over this, that actually give you uh, like 1000 over 8, that's 125, sorry, 125 pi, yeah. So basically that's the solution. You can like use your calculator, or you can do whatever. So that is like, so R would be equal to 5 over cubic root of pi, but like it's just easier, just use the calculator. So if you use the calculator, you can get, okay, this R is equal to, sorry, if you use the calculator, R, not R cube, be equal to 3.41 centimeter. Yeah. So divide this by pi, and you take the cubic root. Okay. And then you'll have like an equation here. So I have like this equation. If I substituted R here in this equation, so you substitute R here in this equation, and then you can solve for H. In that case, I got like H is equal to 13.66 per meter. Yeah. And then, so now you have your R, you have your H. You can substitute here in your objective, in in your objective function here, or like here. You can, this is like your cost function. So or you can just substitute R here, yeah, and then it will give you the cost. So like the cost here will be, that's what I got. If I did this correct, this is what I got. Now you want to, I mean, of course, this is the maximum, like, and how would we know that this is the maximum? If you like, see your R here, you substitute this here, and then you got, uh, sorry, this is the minimum because you want to minimize the cost, like, because why did I know that this is the minimum? Because when I substitute this here, this C will be larger than 0. Larger than 0 means like minimum, yeah? And you know why when the slope is larger, like when the second derivative is larger than 0, it's minimum. Because like at the minimum here, okay, this is the slope here is 0. Okay, but just to the right, a little bit to the right, like this is going up, like, so you have a positive slope. And that is, so positive slope means that you are curving up. Curving up means that you are a minimum, yeah, because you are a minimum, then you go up. Okay, so that is it for this guy, and yeah, see you in the next